Republic. Then he spent some time research position in Texas and in Oxford. And now he returned back to the Czech Republic, where he works in the Institute of Mathematics of Czech Academy of Sciences, and he talks on tensor methods for higher dimensional chemical Fokker-Planck equation.
All right, thank you, Radek, for introduction. And let me thank organizers for inviting me here and for the opportunity to present our talk, and thank you for coming. I noticed that my talk will be quite different from the talks we heard today. First of all, I am not able to speak so quickly as the previous speakers. And second, it will be about mathematics. Okay. In particular, I would like to talk about a numerical method that is capable to solve high-dimensional problems. I mean, high-dimensional PDEs. I will focus on chemical Fokker-Planck equation, but the method is not limited to that. It's more general. It can be applied to general high-dimensional data. Well, and I believe it will be of some interest to you, because if you want to model stochastic chemical systems, you immediately end up with high-dimensional problems, just because the state space where the system lives is higher dimensional. The number of dimensions is the same as the number of chemical species you have in your system. The trouble is that if you try to use standard numerical methods, you have to face the curse of dimensionality, which basically prevents you to use standard methods to solve your problems, just because these problems are too huge. The size of that problem scales exponentially with the dimension, with the number of chemical species. So given any computer you have, you quickly run out of the memory with a relatively small number of chemical species. All right. So in the first part of my talk, I will just introduce my notation, basically. In the second talk, I would like to talk a little bit more about the equation itself, about its posedness, and I will basically define the problem we are solving. And the main part will be the third one, where I will try to explain the tensor methods. My goal is to keep everything as simple as possible and explain the main idea, how we are able to break this curse of dimensionality. And at the end, I will mention our current project about error estimation in this business. Okay, so my aim is to model stochastic behavior of a general chemical system. So this is a way how to write down a general chemical system with n chemical species and m reactions. So this is the reactant part. We have the stoichiometric coefficients of reactants, stoichiometric coefficients of products, the rate constant Kj. And we will model this as a Markov process. So the probability that the J's reaction fires is given by the propensity function alpha. Here is a formula for alpha. So I don't know if you're familiar with. This is just a combinatorial number, so it is the standard way how the propensities look like. Okay, what else? The capital X is a vector of the chemical species, so this corresponds to the number of molecules of the chemical species 1 and so on. And I will need this stoichiometric matrix nu, which is just a difference of these two, nu p minus nu r. All right, so I think this is pretty standard. What we are interested in, it is the probability that the number of molecules at time t is equal to some given vector. So we are okay. So this probability can be computed in different ways. So what we have chosen is the chemical Fokker-Planck equation. This is an equation that somehow approximates this probability. All right. So this is the Fokker-Planck equation. This is written in component-wise notation. So it's quite a horrible formula, right? But this is the diffusion part. This is the drift part. Here is the diffusion coefficient. This is the drift coefficient. I'm used to work with the vector and matrix notation, so I like to see this equation in this form. So this is the same thing, but written in a little bit more compact way. This capital A, it is the diffusion coefficient, and this vector B is this drift coefficient. Here you can see the definitions. Basically, it is just a copy of this. It is the corresponding entry of that matrix. Okay. So I have noticed in some talks here before that some people denote it in the opposite way, that this is the diffusion coefficient is B and the drift coefficient A. So sorry for that. I hope it will not be confusing. Good. So far, so good. What can we say about the well-posedness of that equation? When this equation has a solution, when the solution is unique? Well, it depends, but what can be done really easily is to use the theory of elliptic operators and say, and if that Fokker-Planck operator is elliptic, then we can say that the problem is well posed. And that Fokker-Planck operator is elliptic if this diffusion matrix is symmetric and positive definite. So is it the case or not? Well, sometimes yes, sometimes no. That coefficient, the diffusion coefficient, has a structure. And this is the definition of that diffusion coefficient. And we can see it as a matrix product. This is the product of that stoichiometric matrix nu with the matrix alpha, and that matrix alpha is diagonal, which has the propensity functions as a diagonal entries. So it has a nice structure, and from this structure we can immediately find sufficient conditions for positive definiteness, so for ellipticity. So immediately we can find that if the columns of this stoichiometric matrix nu are linearly independent, and if the propensity functions alpha are positive, then this matrix must be symmetric and positive definite, and the Fokker-Planck operator elliptic, and everything will be well posed. So this is nice. So important condition is the positivity of the propensity functions. Here I have an example. This is a chemical system that we study in one of our papers. It is a system with 2 chemical species and seven reactions. We have some reactions of third order here. And this graph corresponds to the state space. This is the X1 molecule, X1 species, X2 species. And this blue square, this blue domain, corresponds to those points X where this lemma applies, where the propensity functions are positive. Okay, so in this region we have very simple condition. We can easily find this domain, and we know that in this domain our operator is elliptic and everything is fine. If we work a little bit more and investigate the diffusion matrix and find when it is positive definite, we find out that it is a larger domain, drawn in red. And good news is that domain covers all the positive quadrants. So for everywhere in the positive quadrant we have symmetry and positive definiteness. Okay, so now the question is, if we want to solve the Fokker-Planck equation numerically, we cannot solve it in infinite domain. So we have to truncate the domain somehow. And the question is how to do it. We can do it naturally like this. We can align the domain with the axis. But then we have some area here where the diffusion matrix, well, it is symmetric positive definite, so from the mathematical point of view the problem is well posed. But some propensity functions are not positive, which might be a problem from the modeling point of view. Or we can be on the safe side. We can define the domain like this in that in the blue region where all propensity functions are positive, but then we are missing some part of the state space, which again might be a problem. Anyway, what we do, frankly, we solve such systems where it doesn't matter, where the probability mass lies somewhere far away from the boundaries, and we are on the safe side. I will comment on that a little bit later. Okay, there's also a question where to draw these exterior boundaries, right? But there are methods how to find it. All right. So once we choose the domain where to solve our equation, we have to think about boundary conditions. So from the mathematical point of view, the no-flux boundary conditions are very, very natural, because if we have this evolution problem with no-flux boundary conditions and with some initial condition, then this problem is conservative. This no-flux boundary condition implies conservativity. It means that if I start with some probability distribution P0, it means that the integral over P0 is 1. It's probability density. Then this property is preserved for all subsequent times. So integral over P at any time is 1. So this is nice. So this seems like a right boundary condition. Okay, but we are actually more interested about the stationary solution of these problems, not about the time evolution, but what will be the stationary solution. So we just forgot about the time and replaced the time derivative by 0. We keep the no-flux boundary conditions, and we have to impose now. We have now imposed that the integral of the solution must be 1, so it is some normalization condition. The no-flux boundary condition here has again a good meaning, because it guarantees a unique non-trivial solution of this equation. You may notice that the equation always have a trivial solution. Pp equals to 0 just solves the problem, but we are not interested in that. We want some non-zero solution. And having this boundary condition, we can apply Fredholm theory, and we can analyze the adjoint problem to that and come up with the result that is unique for one-dimensional space of non-trivial solutions. Okay, an interesting point of view is that we can see it as an eigenvalue problem. We can see it as a problem of finding eigenfunction p corresponding to 0 eigenvalue. All right. From the practical reasons, okay, later on we will use finite difference method, and we want, and the implementation of no-flux boundary conditions is a little bit complicated with this method. So we wanted to simplify our life and put just Dirichlet boundary condition. So what have we done if we replace the no-flux boundary condition by 0 Dirichlet boundary condition? Well, we did a lot. We changed the problem, and actually the only solution to this problem is just the trivial one, 0. So this is not the right thing to do. But if we look at that thing as an eigenvalue problem, and if we will look for the eigenfunction that corresponds to the smallest eigenvalue, then we are back on tracks, and it has the right structure from the mathematical point of view. And actually this is interesting because the size of this smallest eigenvalue tells us about the error we introduced by imposing these, say, non-natural boundary conditions, and about the choice of the domain omega. If this eigenvalue lambda will be small, then we may be quite certain that the probability density close to the boundary will be close to 0, and we are not committing big errors by these boundary conditions and by the choice of omega. So it is sort of a good indicator whether we are on the good side. All right, so this is the point. This is the problem we will solve. We will try to find a numerical method to solve this problem, assuming that the domain omega is higher dimensional. 4, 5, 6, 7-dimensional domain. All right. We will do it by the standard easy finite difference method. So how it works? We need a mesh, a grid. So we cover our domain by a grid and use that grid points to define finite differences, and we replace our derivatives in the equation by finite differences. And at the end, we obtain a matrix. The operator, the differential operator, will be replaced by a matrix. And instead of differential eigenvalue problem, we just have to solve algebraic eigenvalue problem. And we can use methods of linear algebra to solve it and find that's it. Well, problem is if this domain omega is higher dimensional, as I already mentioned. We are facing the curse of dimensionality. In one dimension, it's pretty simple. If we want some accuracy, we define some mesh size, introduce the mesh, solve it, and that's it. If we want to keep this accuracy in 2D, we need n square nodes in our mesh. If we want to do it in 3D, we need n cube nodes, and so on. So if we have capital N chemical species in our system, we would need lowercase n to the power of capital N nodes or degrees of freedom in our system, and this is that exponential increase in the size of our system. So this is the curse of dimensionality, and let us explain me the main idea of tensor methods that enable to somehow break that curse. So to explain the main idea, I need to understand the concept of tensor product of matrices, or Kronecker product. You may know it well, but let us just recall what is the tensor product of two matrices. So if I have two matrices, I will just take as many copies of matrix B as there are entries in the matrix A. So in this case, I take 4 copies of matrix B and multiply each copy by the corresponding entry from matrix A. So at the end, I obtain a matrix which is 4 by 4, and every entry in this matrix is a product of two numbers, one number from first matrix, second number from the second one, and I have all possible combinations here. Okay, the same thing with vectors. The tensor product of two vectors is just a special case. So again, if I have a tensor product of two vectors, like here, I take 2 copies of the vector B, and the first copy is multiplied by A1, second copy by A2, and I have vector of length 2 by 3, right? 6. And if I multiply 3 vectors, I just do the same thing. If I have a tensor product of 3 vectors, I get a long vector, and every entry in that vector will be a product of 3 numbers, each number from individual vector. Okay, and now we have important observation. Imagine that it's a simple observation, but it's important. Imagine that we have capital N vectors, and all that vector, each of these vectors has size lowercase n. So we have capital N vectors of some size, and we do a tensor product of all these vectors. So we end up with a long vector, and the number of entries in that vector will be just a product of the sizes of these vectors. So it will be lowercase n to the capital N. So what we have done, we had like relatively small number of vectors which are relatively small, and end up with a vector that is huge. And the idea of tensor methods is exactly the opposite. We need to handle some huge vectors, but we will try to approximate them as a tensor product of small number of relatively small vectors. So let me explain you this in more details. And since this is a technically complicated stuff, I would like to simplify it as much as possible. So let us switch from the Fokker-Planck operator to just Poisson equation. So this is a problem that everyone knows well, and it's pretty standard. The only difficulty is that we have n dimensions. Okay. So once again, how do we solve it in one dimension by finite difference method? We introduce a mesh, and we sample the right-hand side in every mesh point, or every node, and obtain a vector capital F of size lowercase n when n corresponds to number of grid points. We do the same with the solution. We sample our approximate solution in every grid point and approximate our the exact solution at point xi by the corresponding entry in that vector. And the idea of the finite difference method is just to replace the derivative by finite differences. So this is the second central finite difference that is used to approximate the second derivative. And I believe that it's clearly visible from the formula that it can be written as a matrix times vector u, right? If I have vector u of these values, I can multiply this vector by this matrix and obtain formulas in this form, right? This number 2 is on the diagonal, this -1 are in this subdiagonal, and this -1 is on the superdiagonal. So basically what I am doing, I will replace this guy on the left-hand side of the differential equation by just this Laplacian matrix. This is called Laplacian matrix, multiplied by the vector u. So doing that, I will transform this differential equation to a system of linear algebraic equations, and since I'm in one dimension, the system is relatively small, I can solve it, everything's fine. Good. So in 1D, it's very standard. What happens in 2D? In 2D, the Laplacian is a sum of two second derivative with respect to the first and second variable. And to explain what's happening, let's imagine for a moment that my solution that I'm looking for can be written as a product of two univariate functions. First function will be just a function of x1, and the second one of just x2. So this is a standard string. So if my exact solution will be in this form, I can substitute in here and see that the Laplacian is just the second derivative of q1, say plus q1 times second derivative of x2. And the point is that this is just a second derivative of a function of just one variable. And I know from the previous slide how to approximate this. It is just that Laplacian matrix multiplied by the corresponding vector q1, right? Where the vector q1, it is the discretization of this function q1 x1. So in the x1 direction, I have some nodal points, and I evaluate this q1 at these nodal points and obtain that vector q1. I do the same thing with q2, but there is no derivative, so it's basically the same thing here. And since the grid has this Cartesian product structure, it is a Cartesian product of two one-dimensional grids, this guy will be just a tensor product of these two vectors. Okay, and the same thing is happening here. This is just the second derivative of the second component, so I multiply q2 by the Laplacian matrix, and utilizing the structure of the grid, I will then find that this is the vector q1 tensor product with dq2. And this is the most important thing for the idea. Then I can just use the standard properties of tensor products and write this one in this form. I can write it as a standard matrix vector multiplication, where that matrix will be this D tensor product with identity plus identity tensor product D, right? This is the matrix, and the vector will be just tensor product of these two vectors. And this is the standard algebraic properties of tensor products. Yes, please.
Both is Q2 is a vector, while none of Q2 is a scalar, correct?
Right, yes.
What's the difference between the two of them?
Thank you for the question. I have a function, say q, this way, q x2, function of one variable, so this is a scalar, and that vector q has entries, and the ith entry of that vector is the value of that function at the ith grid point. Okay, so what I do basically, I take this function. Okay, if I have at x2 direction, I have some grid points in x2 direction, and I sample this function at each grid points, and I obtain that vector bold q2. Okay, thank you.
Excuse me.
Yes,
The
please.
U is defined by Q1 tensor Q2, right? The middle line. The definition of the U. I mean, if U equals to Q1 tensor
Yes.
Q2, isn't it the radical?
You think it should be opposite?
I mean,
No.
you wrote down if U equals to Q1 times Q2.
Yes.
Things like, but it should be tensor between Q1 and Q2.
Here?
Yeah.
No.
No?
This is just a function. This is just a scalar function.
Ah, I see. Okay. Okay.
Okay, and I use the same trick here.
Ah, okay.
Function u is a function of two variables, x1, x2, and and now there is a mess with indices. This is the point that I try to avoid as much as indices as possible, because if you read the literature about the tensor methods, it's a full of long indices, and I try to avoid it because it's like mess up everything. They are there, you know, you have to understand it. So basically what I do here is I have a function of two variables, and I have to sample that function on the two-dimensional grid. So I obtain a vector of size of n squared, and every entry in that vector corresponds to the value of this function and that grid point. Okay, and that long vector bold u is okay. If that function u is just a product like this, then this bold vector u is a tensor product of these vectors. Okay, that's the idea. All right. So in this way, we deduce that this finite difference matrix can be written in this tensor product structure. So at the end, we have a vector matrix times vector equals vector of right hand side. Again, we derive that matrix. Actually, this property here, well, the fact that this matrix A can be written as a tensor product of these smaller matrices is independent of the form of U. I put it here just for illustration, but U can be anything, and you can derive that this matrix A is in this form. Actually, I think it actually follows from this. All right, let's move to the 3 dimensions. Okay, now you see how it works in 2 dimensions, and I think this is the main idea. And I believe that you grab the structure, and you will believe me that in 3 dimensions, that matrix A will be T tensor product with identity times identity plus identity times D identity plus I, D. Okay? Because in 3D, the Laplacian is a sum of 3 terms, second derivative with respect to x1, x2, x3, and these 3 terms corresponds to these 3 approximations. I have just one more variable, so therefore there are 3 terms in the product, and so on. In 4 dimensions, I would have 4 terms, and I will just multiply one more tensor product there. Okay, so in this way we derived that the finite difference matrix A can be written in any dimension in a compact form as a tensor product or a sum of tensor products of small, say, one-dimensional matrices. So I can store the huge matrix in 20, 100 dimensions in a quite compact way. That's the idea how to break the curse of dimensionality. Okay, so this is what we did for the matrix. What about the vector, right? The trouble with these high-dimensional problems is that we cannot store even the vectors. The vectors are so huge that they don't fit to the memory. So we have to do the same trick for vectors as well. So, okay, here I have again the same duality between the functions and vectors. Okay, so the first line corresponds to functions. In general, I want to approximate a function of 3 variables. But the trick here is to assume that such a function can be well approximated by a sum of products of univariate functions. q1 of x1, q2 of x2, q3 of x3. So if I can approximate my exact solution in this form, then on the level of the grid, if I discretize that function, I will, in the same way as before, approximate that vector of values of u at grid points by a sum of tensor product of short vectors where each vector corresponds to one dimension. Okay? So this is called the canonical decomposition of a tensor, and this capital R is a tensor rank. We call it tensor rank. It corresponds to the number of terms in that sum. So if I have just one of these terms, I have rank 1 approximation of that long vector. All right, so how it works then? So in this way, I can have a compact tensor structured storage of my matrix A. I can have a compact form of my vector, and everything boils down to solving such a system of linear algebraic equations. And this is actually the hard part. But I can use some iterative methods to solve such a system, and in these iterative methods what I basically need is just to multiply with the matrix. So if I have some vector stored in that tensor structure, and if I have my matrix stored in that tensor structure, I can do the matrix vector multiplication. But of course I cannot do it as it is written here. I cannot somehow assemble the huge matrix, assemble the huge vector and do the multiplication in a standard way. I have to use the properties of the tensor product and write down this guy as the sum of tensor products of this small vector. You see that this is the matrix D times Q1. It is here. This is identity matrix times Q2. Identity times Q3 is here, and so on. I times Q1, D times Q2, and so on. So it distributes like this. And you may notice that this can be evaluated because this is just a tensor product of matrix vector multiplications, and these matrices and vectors corresponds to one-dimensional approximations, one-dimensional vectors. If they are small, I can do it. So at the end, if I have a vector of this form, I can multiply that vector by a matrix and obtain another vector, the result, which is again in the same form like this. It is a sum of tensor products of some short vectors. So I can store it again. And you also immediately see that there is more terms here. I started with R terms, and here I have 3 times R terms. So the sum here is longer. The tensor rank grows. If I multiply, if I do some algebraic operation with tensor structured data, the tensor rank, I can do it in the tensor formats very, very efficiently, but the tensor ranks grow. And after several operations, it would kill me. I would fill up my memory with all these terms. So therefore, very important operation is the tensor truncation. So this is the heart of all tensor computations, that I have my tensor stored in a tensor format as a sum of tensor products, and I need to approximate it with tensor with the same structure as a tensor product of short vectors, but this tensor rank S must be smaller than R. I have to, but still I have to keep the accuracy. I have to approximate it somehow, but decrease the tensor rank. And this is the crucial operation that has to be done basically after every algebraic operation in the solver. And if you will study this in more detail, you will find out that it's pretty tricky and difficult to do, and you will encounter numerical instability when you will try to do it. So therefore, actually, people don't use these tensor structures. They use a little bit more sophisticated tensor structures, but the basic idea is the same. For example, people develop the tensor train format, which is a little bit more clever structure. You organize your data in a little bit different way, and then you can use that little bit more complicated structure to do this tensor truncation efficiently and in a numerical stable way. This tensor truncation is based on the singular value decomposition of your matrices, which is done dimension by dimension. Okay, so I think this is enough about explanation, the basic idea. And let me show you an example. Let me show you how to solve that Poisson equation in 20 dimensions. Okay, I prepared the MATLAB code. So just for fun, I can run it like this, and voila, I have solved Poisson equation in 20 dimensions. And on this laptop, you just saw it, and it took 2 seconds. Okay. So it can be done. I mean, of course, this is a very suitable problem for that method. So for some problems, I can solve very efficiently.
How many grid points did you have?
Yeah, good question. I forgot to mention. In this case, in these computations you have just saw, I have 128 grid points per dimension, and I had 20 dimensions. So this is the number of degrees of freedom that I have in that system. Okay, but of course I don't store this huge amount of data. I store it in that tensor format. This is quite interesting. I have this data. I solve it. I have the solution in some format, and I can access any point. If I want to evaluate my solution at some point, I can do it. I can use the data, find the corresponding indices, find that value. But I cannot do it for all these points. If I want to do it for all the points, it would kill me. So that's another problem. If I solve it, I have the solution in some format. How to use it? What to do with that? For example, how to plot the result. I cannot plot 20-dimensional function, right? So what I do here is, that I integrate over first 18 variables. I integrate them and end up with a function of 2 variables, x19 and x20, and this is the function that I plot. Okay, so if u would be a probability, if u were the probability, this is just a marginal probability, right? I integrate over all the others. Okay, yes?
I bet you don't really have to evaluate at all the points to do this integration, right?
Pardon?
You don't have to evaluate the function at all the points to do these marginal integrations?
No, that's
a trick, right?
That's a trick. Basically, very good question. I can do some operations with the tensor formats, but I cannot do everything. But integration, I can integrate. Basically, my function is stored as a product of functions. Okay, so that's u1, x1, u2, x2, and so on. So if I do this multiple integral, it splits up to just a product of one-dimensional integrals, which is easy to do. Right? Therefore, I can integrate this very efficiently. Yes.
So what if you replace the 1 with a function f of x? Would you, let's say a simple function of 20 variables, would you still be able to do it in 2 seconds?
Excellent question. Probably not. Of course, this is very important. The data in that equation must have this product structure somehow. Okay, so in general, I need my right-hand side of 20 variables to have some product structure that I can exploit and store it. If it is not the case, I have to approximate it. I have to find some product structure approximation, which is another problem that is studied, and people are trying to find condition what kind of functions I can efficiently approximate this way, which I cannot. So I have to work more if I have general data. Well, on the next slide, I am back with the Fokker-Planck equation. In the Fokker-Planck equation, I don't have right-hand side f, but I have these coefficients f, a and b. And if you write down how this diffusion coefficient and drift coefficient looks like, you end up with such formulas. And you see that these formulas have this nice product structure. It is a sum of something, but it is a product of these, and every term in this product depends on just one variable. So it's exactly the structure that I need, and I can approximate these, not approximate, actually I can express these coefficients in that product structure exactly, and I can build up this finite difference matrix for the Fokker-Planck operator. Well, exactly, actually. It will be, the tensor rank will be somehow proportional to the number of chemical reactions and so on, but it will be some reasonable number, and I can store it. So this is the conclusion, that I can use the trick that I have shown you for the Poisson equation. I can use it for the chemical Fokker-Planck equation as well. It's a little bit more complicated because I have more terms and I have these coefficients, but basically the idea can be put forward, and I can derive the matrix in that tensor format. I can work with these vectors in the same way as before. Another little technical complication is that I don't have just a linear system. I have eigenvalue problem, so I have to solve it somehow, but it can be done. And that's it. So we are able to solve the chemical Fokker-Planck equation in higher dimension. Of course, we don't do everything by ourselves. We use the tensor trained toolbox, TT toolbox, written by Ivan Oseledec and other people. It is a MATLAB toolbox that I use to solve that Poisson problem. Right, we can do even more. We can. You may notice that these equations depends on the rate constants of our chemical reactions, and these rate constants are in reality often unknown. This is the big problem, to estimate the values of these coefficients. So what I can do with this tensor format is that I can basically solve within like one solve the equation for virtually all possible values of that coefficient. I can consider that coefficient as an extra variable, and it will increase the dimension of my system by 1, but I can somehow use the tensor technology to handle this one extra dimension, and I can solve the problem for all possible values of that parameter. And once I have solved it, I can do some post-processing, see what is the solution for different values of this parameter, and do, I don't know, parameter identification or bifurcation analysis or whatever. I can do also some other numerical tricks like multi-level approaches. because this is a partial differential equation solved by finite differences, so I can start with some coarse mesh, solve it on the coarse mesh, which will be quick, get some rough approximation of my solution, then I refine the mesh, take this rough approximation as an initial condition for further computation. So I can use these numerical tricks to accelerate my computations. So all this is fine, and at the end we were able to solve some interesting examples. This is a cell cycle model, like a Fokker-Planck equation for a cell cycle model. It has 6 chemical species, so it corresponds to six dimensions. But we also treated one of these parameters as an extra variable, so in total it was 7-dimensional problem. And Shuo actually, where is he? He's sitting in the audience. He was able to solve it, and these are some results. So for some value of that, these are the marginal probabilities. So for some value of the parameter, we can see unimodal distribution. For some other value of the parameter, we can see some stochastic oscillations. So there must be some bifurcation happening. The same situation written or drawn in different perspective. Here are like 3-dimensional marginal probabilities, and if we look at them, okay, if we marginalize in some way, we see some stochastic oscillations, or we see unimodal here for one value of the parameter, and for other value of parameter we see oscillations. And if we marginalize in a different way, we can see unimodal for the one value of the parameter and bimodal for the second value of the parameter. So you can do bifurcation analysis, for example, with this tool. Okay, so all these things are done in our paper that was published last year. All right, so what we are working on now, we would like to push this idea forward, and we would like to do some error estimation. The point is that these tensor methods, the most difficult part for the tensor methods is to solve the corresponding matrix problem. This is really difficult, and these methods may fail to solve it for various reasons that I will not comment now. But what I believe is possible, and we are working on that, is to estimate the error approximately, a posteriori. So it means you will solve your problem numerically, you will get some numerical solution, and you don't know whether it's correct or not, it's just some picture. So I believe that we will be able to compute some number, some error estimator, that will tell you that the error of this approximation is at most this number that we have computed. So it will be, so if your error estimator will show high values, you will say, okay, something is probably wrong, I have to compute more. We want to go even a little bit further, because what I was talking now was, it was the estimate of the total error. But that error has different components. You know, we have the Fokker-Planck equation does not describe the system exactly. There's some error. I truncated the domain somehow, so I caused some error. I introduced some artificial boundary condition, another type of error. I do this discretization error. I replace the derivatives by finite differences, so that's the discretization error. And by the way, in numerical analysis, we have quite good a posteriori estimates of this one. But then I approximated my long vectors by that tensor structure, but it's again approximation. There's another error that we call tensor error. And then I have to solve the linear algebraic system, which I cannot do exactly again, so there is the algebraic error. And the ultimate goal here is to have some estimates of all components of these errors to see which of these error dominates, or where is the worst problem, what I should investigate, where I should invest more time and more effort to decrease the error. Okay. So for example, if the tensor error dominates, there is no point to refine the mesh, right? So this is what we are working on now. This is our current project. Okay, so this is just my last slide. I have shown you that the tensor approaches can break the curse of dimensionality, and that using these methods we are able to solve what we call parametric chemical Fokker-Planck equation, and this method can be used for bifurcation analysis, for sensitivity analysis, for parameter estimation, and things like that. This tensor approach is not limited to finite differences, as I was talking today. It can be applied to any other discretization method, like finite element method or discontinuous Galerkin method, if you wish. And the tensor methods are not limited to the chemical Fokker-Planck equation only. You can solve, for example, the chemical master equation by tensors, but it would be a little bit different story. Okay, so thank you for your attention.
So my question was the last point.
Okay.
There. I mean, why didn't you try directly trying to solve the master equation? Because once you discretize it, you have finite difference. It looks similar.
Right.
Good. Have you tried it, and how hard or how easy?
Good question. Well, the pragmatic answer is that it was done already before, so we have to do something different. No, this was really done by the group of Christoph Schwab in Zurich, so it's really natural to do it. Okay. Solving Fokker-Planck equation it's a little bit different, you know. For example, in what you cannot do with the master equation is to choose your mesh as you wish. So you cannot do this, for example, that multi-level tricks with numeric. So with the Fokker-Planck equation, we are able to solve larger problems. In fact, with the master, if you solve the master equation, we are somehow limited. So we were able to push the solver a little bit forward. You know, yeah.
But can't you do the same kind of, if you start with the matrix for the master equation,
Yes.
can't you do the same kind of approximation there with a larger mesh and do that directly rather than getting involved with all these problems with the boundary conditions and so on?
With the master equation.
Yeah.
Well, of course, I mean, you can do it. It's a little bit like a philosophy of computing, like what to do for the first and what to do next.
Yeah.
And there are like different paths that you can follow. That's clear. But I don't know if you get your question right, but with the master equation, you cannot refine the mesh as you wish. The mesh is somehow
Well,
given.
I mean, somehow you're approximating the master equation by a differential equation, partial differential equation.
Okay. This is what
And
I
then you're approximating that by,
tensor stuff. Yeah.
so there's some way to go from here to here,
Okay.
okay? Can't you go from here to here without the intermediate step, I guess?
I can. I think this is what I meant by the last point here. I can
Yeah.
really approximate the master equation directly.
Yeah.
But it has some limitations because that in master equation I have to go one molecule by one molecule. My state space is like that. With the Fokker-Planck equation I can do like larger amounts of molecules. My steps, my finite difference steps might be larger, like 10 molecules, 20 molecules. So I can compute like larger systems with Fokker-Planck equation than master equation. So what I'm saying is that with the Fokker-Planck equation, in some cases, you may get further than with the master equation.
Okay. Second question is when you do this, or comment maybe, when you do this boundary condition, then you're solving the eigenvalue problem.
Yes.
What you're solving for is the essentially conditional probability distribution for your diffusion process,
I see.
given that it has never left
Right.
your okay. That may be a reasonable approximation to the stationary distribution for the whole process, or it may not. If I haven't thought about this in the context of master, or chemical reactions. But if you've got ways out one side that somehow there's a circulation that brings you back around, then it might very well turn out to be way off.
Exactly. I agree. I think this is a general problem of the Fokker-Planck equation. Simply for some chemical systems, this is not a good approximation. Yeah. Thank you.
So in the approach you describe, you do not consider any dynamics, right? So, but in this example, you say that there are oscillations that you can detect from your solution. The cell cycle example that you were showing at the end.
I mean that the stationary distribution of my probability has this like circle shape. It means that if I would do many realizations of my process, I would see some like different results, along that circle shape. This is what I meant by like oscillations in that case. But of course, if you want to solve time-dependent problems, you can do it with tensors as well, just with one more dimension.
Okay, I think we have a workshop photo scheduled, so there are local hands here. So maybe let's move on to discussions after, and let's thank all the speakers again. And
Thank you.